Hello, welcome back to my channel. And today we are quickly going to talk about the first week, second term for Ss2 on the channel for the love of chemistry. All right, you're welcome wherever you're tuning in from. Welcome back. So today we are going to look at the first topic, which is rates of chemical reaction. And before we can discuss the rates of chemical reaction, let us quickly remind ourselves what a chemical reaction is. And a chemical reaction involves substances, which we call the reactants, being converted to a new substance, which we call the product. And this conversion happens maybe when the atoms of the reactants are changed, or there is breaking of bonds and there is formation of new ones, or there is a creation of a new substance from the reactant. For instance, when you burn wood, you will never get back wood again. That is a chemical reaction. In a chemical reaction, new substances are formed, while in a physical reaction, no new substances are formed. So basically, a chemical reaction involves the reactants and the products. So, because we know that the chemical reaction involves the reactant, which is the substance that starts the reaction, and the product, which is actually what we get at the end of the reaction, we know without any doubt that a chemical reaction will take place per unit time, because it is not when the reaction starts that all the reactants are now converted to products. So that is why we talk about the rate of chemical reaction. So the rate of chemical reaction deals with how long it takes for the reaction to occur. So how long it takes before these reactants begin to change to products. For instance, if you get wood, you want to burn wood, and then you set it on fire. Sometimes the wood doesn't start burning immediately. Sometimes you have to add more kerosene, add more fuel, or whatever combustion agent you are trying to use to start up the fire. Then eventually, when the wood lights up, the wood don't start turning to ashes immediately. Of course, it takes time before the wood itself starts burning. And when it starts burning, you begin to see stages of the reaction. First, it will be changed to charcoal, and then from there, the charcoal burns down to ashes. And of course, most times, not all the charcoals burn down to ashes. That is what we mean by how long it takes for the reaction to start. Now, the other thing we check at the rate of chemical reaction is how fast the reaction goes. That's how fast does it take this reactant to be converted to products. How fast? The timing for the reactants to be converted to products. That is what we also check in the rate of chemical reaction. And then also in the study of the rates of chemical reaction, we look at how the rates can be measured. And also we look at the pathways in which the reactants are converted into products. So these are the things we look at when we are studying the rate of a chemical reaction. So rates of chemical reaction can be studied in many ways. So the first one is rates of reaction. There are some rates of reaction that are so fast and instantaneous that it can't be measured. There are some reactions that are so fast, before you know what is happening, it has already occurred. So you can't even measure their rate. For instance, when silver, a salt of silver in aqueous solution, which is colorless, reacts with chloride ion to give you a precipitate of silver chloride. This reaction is so fast that the moment you add the silver salt to the chloride, you get a white precipitate immediately, such that the rate at which it's formed is very hard to determine. So you see that the reaction is so fast that you don't even know how to measure it. So the rate of this reaction is very hard to measure because it is very fast and instantaneous. Like as you are adding the chloride salt to the silver salt, you are getting an immediate reaction of the white silver chloride precipitates. Okay, so it is, this particular one is so fast it can be measured. Then some reactions proceed at slow rates that their rates can be monitored. The second one is that it is slow. This one is fast and instantaneous. The other one is slow, then it can be monitored. You can monitor it because it's slow. This one is fast, we cannot monitor it. So for instance, the rates of the decomposition of hydrogen peroxide, the catalytic decomposition of hydrogen peroxide by manganese 4 oxide. So the rate of this reaction is quite slow. With manganese 4 oxide as the catalyst, hydrogen peroxide decomposes to give you water and oxygen. And the rate is slow, so it can be monitored. Then some reactions will not commence unless heat is applied or reactants are ignited. For instance, the decomposition of calcium triazocarbonate 4 during heating. So another type of reaction, this one is fast, this one is slow, then some will not even start unless heat is applied. So for instance, the decomposition of calcium triazocarbonate 4 to give you calcium oxide and carbon 4 oxide. Okay. So this reaction involves heat. It involves heat so that this can decompose to give you this. And then another one is the combustion of petrol or hydrogen by ignition. So the combustion of hydrogen, of course, when you hear combustion, it is reaction with oxygen or removal of hydrogen. So when you hear combustion, reaction with oxygen, to give you water, of course. So these two reactions involve heat. It involves the presence of heat. You ignite this to burn, to give you water. All right, so these are the rates of a reaction. Some are so fast it can't be measured. Some are slow, that it requires catalyst that you can monitor them, and some of them require ignition or heating for it to commence. Now, how do we measure the rate of chemical reaction? How do we measure the rate of chemical reaction? All right, so we have rate of chemical reaction is defined as the change in the quantity of reactants or products per unit time. So rate is defined as the change in the quantity of reactants or products per unit time. So this delta shows change in the reactants or products per unit time. So depending on whichever one you're using to measure it, For instance, if you are using reactant, you will be checking the rate at which the reactant decreases. If you are using product, you will be checking the rate at which the product increases, because when reaction is proceeding, the reactant is moving from being a reactant to becoming a product. So the reactant will be decreasing while the product will be increasing. All right. So the rates, so by definition, we have, you can check the rate of chemical reaction by checking the rate in the change in concentration of reactants or products per unit time at a given temperature. Just like I've said now, the change in concentration of the reactants or products per unit time. So change in concentration all over time, of course at a particular temperature. Then you can also check it with rate is also change in mass of a substance per unit time. This one is concentration, and when we talk about concentration, when it's in an aqueous solution, we are checking the concentration. But then if you are dealing with a solid, another way to check the rate of chemical reaction is by changing the change in mass. Change in mass all over time. So whenever you think of rate, you think of what happens with time. That's what it takes. And then when you are dealing with a gas, you talk about the rate of change in volume of a gas per unit time. So change in volume, this one is for an aqueous solution. Aqueous solution. And change in mass is for solid, while change in volume is for gas. Right. So these are the three ways to measure the rate of a reaction. If it's for solid, it is change in the mass of a substance per unit time, all over the time it takes for that change to occur. If it's for an aqueous solution or for a liquid, it is change in the concentration of the reactant or the product all over the time taken. And then for gas, it is change in the volume of the gas all over the time taken for that change to occur. All this at a given temperature. All right. So the reaction rate is directly proportional to the quantity of the reactant and inversely proportional to the time taken. So if you are to draw a graph of the concentration of reactants and products per unit time. So as time is going, what happens is that if your reactant was here, as time is going, the reactant is coming down because the reactant is being converted to product. When the reaction started, your product was at 0. As time proceeds, the quantity of your product is increasing as time is increasing. So this is your product and this is your reactant. Is it making sense now? So as time is going, the product is increasing while the reactant is decreasing. And the rate of reaction is directly proportional to the quantity of the reactants. Okay? Alright. So if the reactant is much, the rate of the reaction is high. Determination of rate of reaction. Increase in the quantity of product with time. That's how we determine the rate of reaction. Number one, increase in the quantity of products with time. Because we know that as the reaction rates, as the reaction is going on, the reactants are being converted to products. So we can measure the rate of reaction by the increase of quantity of the product with time. So we look at, for instance, looking at the catalytic decomposition of hydrogen peroxide, we can check. For instance, let's look at this reaction. Let's look at this reaction. You have a liquid here, you have a liquid here, you have a gas here. Now, if we want to measure the rate of this reaction, we can simply measure the volume of the oxygen evolved during this reaction. With that, we can be able to check the rate of the reaction by simply measuring the rate of the product, because it is at this decomposes that we get this. So when we measure this, we are able to get the rate of this reaction very quickly. Right. So another way to measure the rate of reaction is loss of mass of the reactant. Loss of mass of the reactant. For instance, let's use an example. When you have zinc, zinc is a solid, reacting with hydrochloric acid in aqueous solution to give you zinc chloride and red hydrogen. To give you zinc chloride and red hydrogen. We can measure the rate of this reaction by checking the loss in mass of this zinc. Because it's a solid, we can easily determine it by loss in mass. Remember when I was explaining the different ways to check the rate of reaction of a solid, a liquid, and a gas? I said that of a solid, you can use change in mass all over time taking for that change to occur at a particular temperature. So looking at this now, zinc is a solid reacting with hydrochloric acid to use zinc chloride and hydrogen gas. So the rate at which this zinc solid is being used up can be used to measure the rate at which this reaction proceeds. Okay, so another way of checking the rate of chemical reaction is the concentration of acid or base in an acid-base titration. The concentration of the acid or base and acid-base titration. You use when a reaction or products, a reactant or product is in aqueous solution of an acid or a base. For example, in an esterification reaction. So, in an esterification reaction in which esters are produced by reacting the organic compound with what? An acid or a base. In that way, we see that the concentration of the acid or the base, as the reaction is going on, there is change in concentration. So that change in concentration is what we check per unit time to determine the rate at which that reaction is happening. So another one is change in pressure of the system. change in pressure of the system. As for instance, a reaction involving gases, example, the decomposition of ammonia. So if ammonia gas decomposes to yield nitrogen gas and hydrogen gas, we realize that when we check the change in pressure, because the more this decomposes, the more of these gases we have. So the pressure of this reduces to give more pressure on this side. We can use the change in the pressure to determine how the rate of the reaction is going. All right, that's another way. Then another way is change in color. Change in color. So for instance, we have the decomposition of dinitrogen 4 oxide. Dinitrogen 4 oxide is colorless, decomposing to give you nitrogen 4 oxide, sorry. Dinitrogen 4 oxide decomposing to give you nitrogen 4 oxide. To give you nitrogen 4 oxide, this is colorless, but this is brown. So, because you know that you started with a colorless solution, the rate at which the color changes can be used to determine the rate of this reaction. So, the fastness of the color change will tell you how fast or how slow the reaction is. And there are so many other reactions that has to do with color change, and with that you can determine the rate of the reaction. All right, so number 6 is mass of precipitate. Mass of precipitate. What is the mass of the precipitate? So we have triosol sulfate 4 ion reacting with hydrogen ion to give water and sulfur 4 oxide and sulfur. We have sulfur is yellow. It's a yellow precipitate of sulfur. Now, when we look at this, the rate at which this yellow precipitate of sulfur is formed will help us in determining the rate of this reaction. Is that clear? Also, we have pH measurement, and in this case, reactions involving color solution of an acid or a base, we can measure the pH of the reaction. We can measure the pH of the reaction, and with that we can determine the rate of the chemical reaction. Now let's look at 1 or 2 calculations involved in this. Calculations under the rate of chemical reaction. Calculations. So the question says a marble chip weighing 4 grams were dropped in a large volume of hydrochloric acid. 2.5 grams of the marble chip remained after 5 minutes. Calculate the rate of the reaction. Alright, remember rate of reaction is equals to what? Where we are dealing with a solid, so the solution will be change in mass all over time taken. Now we get our parameters. Change in mass. Change in mass. We had 4 grams at the beginning of the reaction, and at the end of 5 minutes we have 2.5 grams. So our change in mass will be 4 grams minus 2.5, which will give us 1.5 grams. And then for the time, we have 5 minutes, but we don't solve with minutes, we solve with seconds. So 5 times 60, to change it to seconds, to give us 300 seconds. So our change in mass over time taken is equals to 1.5 all over 300, which will give us what? 0.005 gram per second. 0.005 gram per second. Gram on top, second under. So, in case you don't know the unit, it's very easy to find. If this is a gram and this is a second, and this is over. So, this is gram per second. So, in case you don't know the unit, it's very easy. Because it's always, for instance, if this is concentration, it will be what? Conc over gram. To the concentration over gram. You will not say, concentration over time. I say conc over gram. So to the concentration over time. So what was I saying? Alright, so then we change to 3 significant figure because that's the YX standard. Anyway, it's in 3 significant figure. 1, 2, 3. It's in 3 significant figure. Or you can do 5.0 times 10 raised to power minus 3 gram per second. 3 significant figure. 5.00, sorry. 3 significant, 5.00. Okay, so I don't know if you have any more question on this, you can ask. I will be glad to answer all your questions. And that will be all for today on the rate of chemical reaction. Thank you very much and have a beautiful, beautiful day. Bye-bye.